Improvements in asteroid detection could save us from catastrophe. Daniel Brown reports, astronomers getting better and better at detecting asteroids, and this could one day save us all. On September 4th, 2024, astronomers discovered an asteroid about 3 feet, 1 meter in diameter, heading towards Earth. The space rock would burn up harmlessly in the atmosphere near the Philippines later that day, officials announced. Nevertheless, it produced a spectacular fireball that was shared in videos posted on social media. The object known as RW1 was only the 9th asteroid to be spotted before impact, but what of much bigger, more dangerous asteroids? Would our warning systems be able to detect all the asteroids that are capable of threatening us on the ground? Asteroid impacts have influenced every large body in our solar system. They shape their appearance, alter their chemical abundance, and in the case of our own planet, at the very least, they helped kickstart the formation of life. But these same events can also disrupt ecosystems, wiping out life, as they did 66 million years ago, when a 10-kilometer space rock that's 6 miles contributed to the extinction of the dinosaurs, excluding birds. Asteroids are the material left over from the formation of our solar system that was not incorporated into planets and moons. They come in all shapes and sizes. Their paths are determined by gravity and can to some extent be predicted. Of particular interest are the objects that are close to Earth's orbit, called near-Earth objects, NEOs. As of September 2024, we know of approximately 36,000 such objects, ranging in size from several meters to a few kilometers. But statistical models predict nearly 1 billion such objects should exist, and we only know of a very few of them. We've been monitoring these asteroids since the 1980s and setting up more detailed surveys of them since the 1990s. The surveys use telescopes to make observations of the entire sky every night and then compare images of the same region on different dates. Astronomers are interested in whether, in the same area of the sky, something has moved with respect to the stars from one night to another. Anything that has moved could be an asteroid. Observing its position over a longer period allows team members to determine its exact path. This in turn enables them to predict where it will be in the future, though such data collection and analysis is a time-consuming process that requires patience. It's made even more challenging by the fact that there are many more smaller objects out there than bigger ones. Some of these smaller objects are, nevertheless, of sufficient size to cause damage on Earth, so we still need to monitor them. They're also reasonably faint and therefore harder to see with telescopes. It can be difficult to predict the paths of smaller objects long into the future. This is because they have gravitational interactions with all other objects in the solar system. Even a small gravitational tug on a smaller object can, over time, alter its future orbit in unpredictable ways. Funding is crucial in this effort to detect dangerous asteroids and predict their paths. In 2023, NASA allocated $90 million to hunt for near-Earth objects, NEOs. There are several missions being developed to detect hazardous objects from space. For example, the Sutter Ultra project and NASA's NEO-Survey infrared telescope mission. There are even space missions to explore realistic scenarios for altering the paths of asteroids, such as the DART mission. DART crashed into the asteroid's moon so that scientists could measure the changes in its path. It showed that it was indeed possible in principle to alter the course of an asteroid by crashing a spacecraft into it, but we're still far from a concrete solution that could be used in the event of a large asteroid that was really threatening our Earth. Detection programs create a huge amount of image data every day, which is challenging for astronomers to work through quickly. However, AI could help. Advanced algorithms could automate the process to a greater degree. And science projects can also open up the task of sorting through the data to the public. Our current efforts are working, as demonstrated by the detection of the relatively small asteroid RW1. It was only discovered briefly before it struck our Earth, but gives us hope that we are on the right track. Asteroids less than 25 meters in diameter generally burn up before they can cause any damage, but objects from 25 to 1,000 meters in diameter are large enough to get through our atmosphere and cause localized damage. The extent of this damage depends upon the properties of the object and the area where it will hit, but an asteroid of 140 meters in size could cause widespread destruction if it hit a city. Luckily, collisions with asteroids in the size range are less frequent than for smaller objects. A 140-meter diameter object should hit Earth every 2,000 years. As of 2023, statistical models suggest that we know of 38% of all existing near-Earth objects with a size of 140 meters or larger. With a new US Vera Rubin 8.5-meter telescope that will go into use next year, we hope to increase this fraction to roughly 60% by 2025. NASA's NEO-Surveyor infrared telescope could identify 76% of asteroids 140 meters in size or bigger by 2027. Asteroids larger than 1 kilometer in size have the ability to cause damage on a global scale, similar to the one that helped wipe out the dinosaurs. These asteroids are much rarer but easier to spot. Since 2011, we think we have detected 98% of these objects. Less comforting is the fact that we have no current realistic proposal for diverting its path. In other words, we can't stop them. Though missions like DART are a start, we might eventually be able to compile a near-complete list of all possible asteroids that could cause global impacts on Earth. It's much less likely that we will ever detect every object that could cause localized damage on Earth, such as destroying a city. We can only continue to monitor what's out there, creating a warning system that will allow us to prepare and react. This is from the conversation here under Creative Commons by Daniel Brown, lecturer in astronomy, Nottingham Trent University, on Unexplained Mysteries by T.K. Randall. Please leave your comments, and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.